Most interesting problems involve higher dimensional training data. What do we mean by that? Well, it's common for the training data variable x to be higher dimensional than just a scalar. Let's expand on the baseball example earlier. Rather than thinking of the rebound velocity as just a function of impact velocity, it's a function of impact velocity, barrel diameter, and wall thickness for a collection of composite baseball bats that otherwise have the same designs. So the data would actually have four components: impact velocity, barrel diameter, wall thickness, and the subsequent rebound velocity, all still obtained, let's say, in an experimental lab apparatus. We'll treat V, D, and T, the impact velocity, barrel diameter, and wall thickness, as the x, and the rebound velocity, r, as y. Let's write some notation for the three-dimensional x. The first training point consists of three numbers: an impact velocity, a barrel diameter, and a wall thickness. Those are all thought of as components of x, so let's write that as x1, x2, x3 for velocity, barrel diameter, and wall thickness, but with a superscript 1 to indicate this is the first training point. At the second training point, there's another velocity, barrel diameter, and wall thickness. Those are components of a 3 by 1 x vector, x1, x2, x3, but these are at the second training point. That's what the superscript 2 is. And so on. Finally, there's the last training point, the nth velocity, nth barrel diameter, nth wall thickness. Again, those are the components of a 3 by 1 x vector. This is the nth such point. That's what the superscript cap n is for. Pictorially, we have impact velocity, barrel diameter, and wall thickness drawn in a Cartesian coordinate system, and pictured is the location of these values at the ith training point. The ith training point is a 3 by 1 vector of real numbers. Generalizing this, what will our notation be for n data points of n-dimensional data? Over here in the baseball example, we had n data points of 3-dimensional data. So in generalizing this, the 3 will simply become a lowercase n. The superscript represents the counter on the data points. So that's the first data point, the second data point, and finally the nth data point. Remember, we have n data points. Each data point, though, consists of n-dimensional data. So the first data point actually has n components. In the baseball example, it had 3 components. Here are the n components, x1 through xn, all associated with the first data point. The second data point also has n components, x1 through xn, but these are associated with the second data point. Finally, the capital nth data point has lowercase n components, x1, x2, xn, and these are all associated with the capital nth data point. Conceptually, this is not difficult, but making sure the notation is clear does require some attention to detail. Let's use this notation to set up a regression for high-dimensional training data where the basis functions include the constant function and all linear functions. So, as I mentioned, we'll suppose that the approximating function class is all affine functions of x. That's written here as f sub ab of x equaling a1 times x1 plus a2 times x2 plus an times xn. Remember, x has n independent components, plus b, for any choice of parameters a and b. And remember that a is a parameter vector, a1 through an. In terms of basis functions, the first basis function, phi1 of x, is just the first component of x. The second basis function, phi2 of x, is the second component of x. And the nth basis function, phi n of x, is simply the nth component of x. Finally, the n plus 1th basis function is 1, and that's what leads to the constant b term. With the training set, the errors in the fit are defined as usual. It's the approximating function evaluated at the ith training x minus the y value at the ith training point. Substituting what the approximating function is gives this error explicitly in terms of the choice of a and b. Again, this can be written in vector form involving the matrix vector product of a known matrix, which involves the basis functions and the x coordinates of all the training points, and the vector is the unknown coefficients forming the linear combination of the basis functions. As we've seen many times, the error criterion says to choose A and B to minimize the norm of E, and as before, this gives a least squares problem. I'll let you think about how the code would be laid out. It's not too challenging, and it's related to one of your lab assignments. The hardest thing here is just to keep track of the difference between the dimension of the space, which is lowercase n, and the number of training points, which is capital N. I've chosen one notation here to keep it straight for myself. You may actually prefer a different notation. In any case, this is the least squares problem that solves for the optimal affine function fitting a multidimensional data set.